Broglie's. And what he did is he said wavelength equals h over p. So what's interesting about that? What is that? What things does this assign a wavelength to that is kind of weird?
Us.
All masses.
To particles, things with masses. See how that is? I mean, normally we would think wavelength like light. But now de Broglie is assigning a wavelength to things. Alright? That's big. So things have wavelengths. And that's, again, treating it like a wave. But in 1924, here's where, so now starts Heisenberg. So we kind of go like this. 1924, Heisenberg. And then over here, Schrodinger. Okay, Schrodinger goes by suggestion by Peter Debye. So what happened is Schrodinger was showing off de Broglie's wavelength. Peter Debye said to Schrodinger, well, if the wavelength's so good, where's the wave equation? Okay, so that was Schrodinger, right? So he goes and does his thing. Heisenberg is his thing. Go ahead.
He did his thing. The mountains.
Yeah, we'll mention that. Quest to understand the guts of Bohr atom. I won't go through all the details. So look, that's why I went all the way through the Heisenberg atom. Heisenberg now says, look, there's too many hand-waving things going on in the Heisenberg atom. I want to solve the Bohr atom. I want to find out what's really going on with the Bohr atom. I want to find out why it works, why it's true. You know, and what I sometimes call an ab initio, from the beginning understanding. All right. At the same time, Schrodinger is going by this. He's propelled by the wave equation, this statement by Peter Debye, where's the wavelength? All right, so the stories that Mike mentioned, so it has been written that Schrodinger then went up into the mountains with a partner who wasn't his wife, all right, and went up to the mountains with this partner, and then came down from the mountains with Schrodinger's equation, all right? So that was 1926. You know, sometime after that. So he came out with Schrodinger's equation. And Schrodinger's equation looks like this. H psi equals IH partial psi with respect to t. Alright, and it was based on the wavelength. Heisenberg, on the other hand, the story, I want you to read the story because it's great. You know, 1900, Max Born was at Germany. And Max Born was goofing around with Hilbert, David Hilbert, and Minkowski. So these were all mathematicians that Max Born was hanging out with. He was a scribe for those great mathematicians at the time. All right, and then he was a professor, and in 1921 he had two students, and his two students were Wolfgang Pauli and Werner Heisenberg. I mean, these are pretty good students, but they were all under the influence of Born, who was under the influence of all those great mathematicians. All right, and then Heisenberg, after he goes out to understand the old quantum mechanics, the Bohr atom, and he goes someplace and he gets hay fever, and he can't work with the hay fever, so he retreats to an island where there's no hay fever, where his hay fever was subsided. And then he came back, and when he came back with, and by the way, this is called a wave formalism. All right? And Heisenberg went off to the islands with his hay fever, and he came back with a matrix formalism. And it can be written like this, like H psi equals IH psi. All right, and so both of these reproduced. These both reproduced Bohr's H atom at a deeper level. All right, and again, you know, the Schrodinger's approach was very wave-like. It turned out that Heisenberg was very mathematical, and while he didn't know it, when he came back, he actually gave his results back to Born, and Born had another student, his name was Pascal Jordan, who was a Nazi, all right, or who history links to Nazi sympathies. All right, that's why I want you to read this. It's a great read.
Yeah, it was a long read, but it was a good read.
It was long, yeah, but it's kind of interesting to hear all these names and everything.
How that played to Born not getting
and how Pascal Jordan never got a Nobel Prize.
Yeah, but they said that may have even affected
and that may have been why.
Yeah.
And then Born wasn't given it right away because he was associated with Pascal so closely. So then Born did something else, which is probabilistic interpretation, and he got it for that. And the other thing they didn't put in here is Max Born is the grandfather of my favorite singer, Olivia Newton-John. Is it in there?
Like the first page.
Oh, okay. All right, yeah.
That's what we the second or third.
Oh, okay. Olivia rocks. All right.
So let's show how who proved that these two formalisms were equivalent.
Okay, so then you have these two formalisms in Heisenberg, and so here let me just give you a philosophical thing. People like Schrodinger and Einstein liked this view because it gave them something physical, gave them a wave equation that they could argue and see, right? But at some point, that whole argument falls apart and you can't use it anyway. Heisenberg, on the other hand, said, look, there is nothing to see, all right? It's mathematical. Here are my matrices. There's nothing to see. Shut up and calculate. All right? And so those were the two very different philosophical approaches. And they look much different than this. I'm kind of giving the modern version. They're very close to the same. But then Jeremy mentioned there's two versions of, you know, the same physics. So what happens in physics if you have two theories? Is it any good? You know, it's worse if you have a million, which is what happened to string theory at some point, right? And it's terrible if you have a million answers, which is some version of string theories are at right now. So it's very unsatisfying to have two different versions. All right, so in 1926, shortly after this, Schrodinger, in fact, showed that these two were identical. All right, now, how did he show they were identical? This is a little bit of modern physics, all right? But here's the scoop. Everybody ready? Okay. The solution to Schrodinger's wave equation, the size of square integrable functions. So the solutions are square integrable. I'm not sure about the spelling of the word itself. All right? Which means that when you take the integral of psi star psi dx, that is finite.
That clock's wrong. It's 11. It's 10:40.
When did we get that? 10:45, right? No?
No.
Okay, 10:45-ish. All right. Now some math. All right. Square integrable functions form what's called a Hilbert space. Now look, Hilbert was one of the mathematicians that was mentioned in the art. That's why
he mentored Born.
It was so nice. It's like it just shows this nice circle. It does need a little bit of explanation. That's why I'm going for it. All right, but Hilbert, they're called Hilbert space, and these functions are called Hilbert spaces. So Hilbert spaces. kind of funky. This has to do with Fourier. You know, you'll see me talk about this many, many times again. Okay, and we're going to talk about it later on in quantum mechanics. All right. But Hilbert spaces are made out of functions, and those functions have all the properties of vectors. So that's the big kicker. Hilbert spaces have all the property of what are called vector spaces. All right? Now, if I have a vector, I can also represent a vector as a matrix, and there's the connection. So Hilbert spaces have all the properties of vector spaces. And vector spaces can be represented as matrices. Okay, so once you get that representation in terms of matrices, it takes you all the way back to the matrix formalism. Alright. So I know this is a little historical and a little bit boring. We're not shutting up and calculating, but I think this perspective is important. Right? So we're going to now do Schrodinger's equation, and I've got a couple minutes to talk about Schrodinger's equation. All right? Great. All right, so I am now going to concentrate on this stuff. Where's the equation? And again, I'll probably do it in more detail tomorrow. Okay. Okay, so light equal wave plus particle, electrons equal wave plus particle. Okay, so the big question now, thanks, Eric, I didn't see it. I heard it.
The cat fell into the electric.
Thank you. Okay, so the big kicker here is now, you know, the Broglie wavelength, that things, that electrons that have mass have a wavelength h over p. And then divide, where's the wave equation? Right? So if you're Schrodinger, what wave equation do you think you got? Well, there's only one wave equation, but we're drawing the connections between electrons and light, right? So if you're Schrodinger, what wave equation prototypical system?
We use one for light.
Light. So start with light. You know, and so that's what we're going to do. So let's do it. So start with light. Okay. The way you get your wave equation for light is, what do? How many have had E and M? I think this is E and M 2. How many have E and M 2? Okay. What are the equations that govern light? Maxwell's equation. So, everybody recite it. Go ahead. First one. Start with the divergence.
Divergence of the electric field.
Divergence of the electric field is rho free over epsilon naught. So again, I'm saying, I know I have people of all different experiences here. So trust me, I don't think that if this is your, you know, that I don't think everybody should have this. But if you're more experienced and taking more courses, in particular if you've had me before,
Divergence of the magnetic field is zero.
you should be able to write down this. So I also think that every physics major, any piece of graffiti they can get to should write down Maxwell's equation. All right? Don't quote me on that. Wouldn't it be nice to be driving on the subway and see Maxwell's equations?
little bit nicer than
I had a bumper sticker like that.